Okay, what I'm going to do first is go over the thing I just gave back to you all on the in-class form. Um, some of you got it all the way correct, which is good. Some of you got it halfway right, so I'm going to explain. All right. Okay. So I think some of you made a slight error here because you all thought that this k over n is the total probability has to be 1. That's not correct. Because 95% of the time, nothing's going to happen. You only have a loss 5% probability, and therefore, after that you know there is a loss, then the loss amount probability is k over n. So what you should have done is this, all right? And I have noted on your solutions as well. So if you look at my tree here, there's actually a 95% chance that there's no loss. Nothing happened. But then the remaining scenarios are there's a loss of 1 or 2 up to 5. These have the probabilities k over 2 to k over 5, like that. In other words, these should add up to how much? These probabilities should add up to 0.05, not 1. That's the only mistake that you had. Because that made your k wrong. And because of that, what is the gain? Okay, this was that thing that caused some confusion the last, well, not confusion, but it was quite difficult to imagine. If you, okay, so if you don't like this kind of function, you can. I'm just leaving it as what's the premium that you should charge. So if you charge X, right, you gain nothing because there's a high probability that nothing's going to happen. And because of the deductible sitting there, even when you have a loss of 2, you don't get paid anything because of the deductible. And then when you have a loss of 3, you still lose 1 because you have the deductible there. So your loss is 3, but you have to bear 2 of it, so you still are down 1. And but then and it's quite obvious. If your loss is 4 or 5, then it's x minus 2 and on. So if you work it out slowly, the expected gain, I know I did it a slightly different way. You can do it the way you did, which is fine. But the whole point is to understand the deductible nature. A deductible means that if the loss is up to that amount, you get nothing. And above that, what you get is less the deductible. So even if you lost 3, you only get 1. Okay? So I want to make that clear. That's how deductibles work. So I think let's go on with our slide. Now, I think it's, do I have anything to talk about here? Let me see. Yes. So we introduced the variance the last time. I'll just reiterate. The variance of a random variable is defined as the expected value of its square. Subtract the square with me. All right. The variance is a more useful mathematical object than the standard deviation. Although the standard deviation is easier for people to understand because the unit is the same as the measurement. Variance is squared. But a lot of mathematical theorems are around the variance, not the SD. So that's why you need to know both. The SD is just the square root of the variance. That's it. Okay. So let's look at some examples. Find the variance of the random variable whose probability distribution is this easy one. 1 minus 1. It only takes 2 values and both with probability half. Very, very easy. Now let me teach you a little cheat thing. You know that to find variance, you need to find both EX and EX squared, right? That's what the formula entails. Do you know that you can actually tell that EX has to be 0? Can anyone tell me why? Is it intuitive to you why the expected value of X, when X is like this, has to be 0? Does anyone know why? Yes, but why is it so beautifully just the mean of the two values that X could be? Yeah, that's right. This is what we call a symmetric random variable. It takes both ends, 1 and minus 1, with equal probability. So intuitively, the mean has to be 0. Imagine a seesaw, okay? One person sitting at 1, one person sitting at -1, and they're the same weight. What's the mean? 0. It has to be symmetric though, okay, at 0. If not, then you have to work it out. But here I worked it out. 1 times half plus -1 times half, which of course is 0. But there's no such thing for EX square, obviously. EX square is a different ball game altogether. You square the 1, that's why I'm giving you this example. EX square is found this way. You take your x, but you square it. So 1 squared -1 also squared, and you see, you get 1. Which makes sense. The expected value of x squared should not be 0 because you're squaring it. I hope this is intuitive as well. Ex squared should not be 0. Yes, the mean, the middle is 0, but the expected value of the square, in fact, actually, is this intuitive to you? Why is the expected value of x squared 1? What can x be? X can either be 1 or -1. When you square that, what can you be? No, if a random variable, x squared is also a random variable. If you're always 1, don't you expect to be 1? So it's actually very intuitive. And so the variance is this minus 0 squared, which is moved. So it's 1. So this is a very simple, but you know, the reason why I'm giving this example is because you have to be very careful with minus signs for expected values. For EX squared, because you're squaring, the minus disappears, but not for expected values, right? I want you to try this. It's not a difficult question. You can just work this out on your own. Rolling one die, x is the number of the face that comes up. Find the variance and SD of x. Can you quickly work this out? First, find the mean, right? If you want variance, you have to find the mean first. Do you know what this is intuitively? When you roll a die with 6 sides, that's fair. What is the expected face that you see? What's the expected score when you roll a die and it's 6 sides and it's fair? Is it obvious? Yes. 3.5. See, due to the symmetricity of the random variable, you know that the expected score when you roll a die that's fair with 6 sides is 3.5. So you already have EX. But you see, for variance, you have to find EX squared. That takes a little bit more work, not a lot, a little bit. So can you do that? Go find EX squared for where X is the score on the die after one roll. So what's EX squared? Right? Not very hard, just a bit of arithmetic. Right? It's a small enough sum that you don't actually need to use any formulas. If you want to use a formula, you can for sums of squares of numbers, but you don't have to. Right? It's quite a small number. It's not that many things to add up, so it should be okay. Okay, do you have something? So okay, so look at how I've done this case. EX we've already talked about. You don't even need to do it if you can work it out in your mind. Due to the fact that the die is fair, everyone is weighted 1/6, so the expected score is 3.5. EX squared, same thing, but square all the x's and that's your variance. And the SD is nothing more than just taking the square root of that thing. Now let me introduce a symbol to you. In case you didn't know, the population mean, EX, has a traditional symbol for its Greek. Does anyone know what it is? Any of you tutoring intro stat students will know that we introduced this symbol. So if you didn't know, I'll tell you. The mean is sometimes written as a mean. And the SD as a symbol. Now, some of you may ask, why is it not S in X bar? Those are reserved for sample statistics. This is at a population level that you're doing things. Because you notice, this is long run. When you do things that expected value, it's long run. So that's why we use Greek letters. At Hope, we have this very established tradition of using Greek letters for long run things and English letters for things that are from the sample. So when I ask you questions like, what's the expected score when you roll a die? We're not saying, yeah, roll the die 30 times and tell me your score. That's short run. Long run, probability is always long run. So that's what we do. All right? Okay, let's go on. A probability distribution of the claim sizes for an auto policy is given in the table below. What percentage of claims are within one standard deviation of the mean? All right, so how do you do things like it? We can try to think of it. So the first thing you need to do is, well, go find the SD of the claim size. Go find the mean claim size and the SD claim size. A bit of arithmetic here, but I think it's not going to hurt you to do this. You can do it on your own, right? Go find the mean quickly. You don't have to even write things down. Just use your calculator and multiply across, right? There's no shortcut here, unfortunately. So of course, on the exam, I will not ask you such tedious questions. I'm not trying to test whether you know how to use your calculator. Okay. But this is not an exam. So there's no shortcut. There's no symmetricity in this probability distribution. So you have to do it from scratch. Right? There's no easy way to get the mean. But the point is to be able to realize you should always do EX and EX squared before you can find the SD. Okay, give it a minute or so. Right? The reason why I ask students to do some of these things is because until you get your hands dirty and do it, it's easier to retain the information if you actually do it. I know it's quite basic. It is. It's mostly arithmetic, but it's good for you to practice doing it so it goes in, right? The definition. So EX, first of all, like that. I didn't even want to write everything out, all right? You should have gotten 55 as your expected claim amount. Then automatically go find EX squared, which is, well, square all the x's scaled by the probabilities. That gives you EX squared. SD is the square root of the variance. So to find the variance, you just take the EX squared minus EX, expected value of X squared. And the only one I want to emphasize is, do you know what the question is actually asking? So the question is asking for, what is the probability that the claim is within one standard deviation of the mean? Did you interpret it this way? Let me explain. What is the probability that the claim is going to be between the one standard deviation of the mean? You will hear this kind of language quite a lot. If people say within one standard deviation, within two, then this is what it means. So here's the mean. Here's one standard deviation. So it means between this and this. So how do you interpret this question? Well, you need to know what these are and then search the table. What is the probability that the claim is between these two numbers? So you just add up the corresponding probabilities for those that qualify. So you can see that 50 minus 20, 55 minus 21 is about 33, like that. So you know that means basically you add up the cases for 40, 50, 60, and 70. You might say, what is the use of this kind of thing? Well, people always want to know. You have a huge distribution of claims. We want to know how likely a claim is to be given a certain set of problems. Right? So quite basic, these things, right? Not very difficult at all. So let's see if there's anything else I need to say. Yeah, I tell you what, I think we will just clear some things up before we do any more examples, and then we are done with this chapter. So, yeah, this is something very, very important. Again, you can prove it if you want to, but the proof is a little bit slow. You have to go like, what's EX, what's EX squared? Basically, if you have the variance of a random variable X, and for some reason, you want the variance of now AX plus B. This is some constant, okay? What's the rule? The A gets squared and then you multiply by the variance. Notice also that the B is gone. Why? Does adding something constant to a random variable change its variability? No, it's no more variable by adding a constant. It's kind of like everyone is on the floor here at a certain height. If everyone climbed onto the table, would we all be the same height? That's it, everyone's on the table now. That's exactly what's going on here. Everyone now steps on a table, the variability in height is still the same. That's why the B does not appear here, but the A comes out as a square. Remember that. I want to immediately contrast with an earlier formula that I gave, which is this one. Notice E of AX plus B. This one, the A does not get squared, and the B is retained. Because if I say everyone now steps on the table, everyone is now higher by a certain height. The variability doesn't change just because we're standing on a table, but did we all get taller by standing on a table? Yes. So the B does appear in an expected value formula, but in a variance, it doesn't. Because variability doesn't change by adding a constant to what a random variable was. And that makes sense. Right? You're not more variable by adding something to everyone. The variability stays the same. Yes, the mean has shifted. As I said, if you all step on a table, we're all taller now. Everyone moves up the same amount, but variability does not change just because we're standing on a table now. All right? Okay, so let's do a few more examples. Suppose that X is a discrete random variable, because that's the only one we've been talking about all this while. And a discrete random variable, find the value of C. Can I have you do that? Right? If I say X is a discrete random variable that can only take 4 values, is it easy to identify C? Can you do it quickly? And what should C be so that this is a valid probability function? You know that a valid probability function has to sum to, for something to pass as a probability function, it has to sum to what? So do that. And the mass is given by Cx squared. Okay. So find C first. Okay, what do you have for C? You should see that you get C by doing this. C x squared, 1 squared, 2 squared, 3 squared, sum to 1. So C is 1 out of 30, first of all. And is EX easy to find? Of course, EX is, these are the probabilities, right? 1 square over 30, 2 square over 30, 3 square over 30. These are the probabilities. But why am I doing 1, 2, 3? Because these are the X values. So the X values are this. So I don't want to dwell too much on this. Very, very easy. How do you find EXX minus 1? EXX minus 1. I have never told you when you have a product that you can split up. So don't do things that you don't know. Use algebra. X squared, X times X minus 1 is X squared minus X. And this one you can split. Linearity of expected values means you can do EX squared minus X. That you can. Plus or minus, you can split up in the expected value. Even this actually is assuming something which I've not told you. Technically, you're not allowed to do this. you know what you actually needed to do? You need to do x squared minus x directly as the function of interest and scale probability. But I'm letting you know, letting the cat out of the bag, that it is okay to break up a plus and minus sign practically. That intuition is correct. But what would be wrong is for you to say things like E of x times x minus 1. This is EX times EX minus 1. These things are not correct. So that's where these things break down. I don't know whether this subtle point is getting through to the class. I'm going to say, actually, when you learn a new operator, you actually are not allowed to do anything unless you're authorized to do it. So I'm authorizing you to say that I'm telling you, you can break up a minus sign and do it separately as ex squared minus ex. But I've not proven that yet. I'm telling you that's the thing, you can do that. But if you want to be very, and one of the keys to success in real analysis is actually never doing things that you're not told that you can do. That's one thing that makes real analysis difficult for most of us. We tend to do things that make sense to us intuitively, but you are never authorized to do it. So the way to do this is actually go back to the first definition. The expected value of anything is you take these values, scale by the probability, but you can find that you do get numerically the same. Then the variance is found the usual way, ex squared minus the square of e x, and you get the answer. So here's the ICP I want you to do now. Can you try? Oh, you know what? Let's have you do. Can you generate a problem like this? Generate a problem like this, and I want you to ask yourself things like this. All right. Never a pen when you need one. I don't know why I stopped bringing pens to class. Okay. Uh, let me call out a. Oh, okay. Let me get a. Okay. I want you to do that kind of question, but ask a few additional things. What is the variance of the random variable that you picked? Okay, do these specific things. Find the variance of negative 5x, the expected value of 7x minus 3. Just demonstrate to me that you know what you're doing. And also compute E, E SQRT x, compute var SQRT x. Okay, and there's a point for me telling you to do that. All right, can you do this? So I want you to generate your own example that looks like this problem. You don't have to stop at 4, or you can go down to 3 if you want. You don't even have to use 1, 2, and 3. You can knock yourself out. You do anything you want. Just make sure it's a finite range. Okay, don't tax yourself by doing an infinite range kind of thing. Something similar in structure. Find the constant. Then, yeah, you need to find ex and stuff like that. Okay, so basically, it's repeat this question for your own probability, basically, right? Which is very similar to this, but not exactly the same. And then additionally do these things, okay? Compute these things as well. Sorry, it should not be. It's quite funny.
Oh, yeah. Oh, I see.
Okay, so the purpose of me asking you to do this and this, these are quite straightforward from what I just told you. Are you confused by this? I hope not. E of square root of x, take square root of x as your function of interest. And then bar square root x, same definition. E of this thing square. And of course, the square of the square root of x is e. So in other words, the variance of this is e x actually minus the square of e square root x. So just follow the definition. All right. So let's move on. You can always hand this into me later. That's okay. Okay. So we're going to look at a slight generalization of where we come from. We're going to look at what happens if you have more than one random variable. So this is where you have jointly distributed random variables, and that's what we're going to get into now. Okay. So first of all, we're going to talk about jointly distributed discrete. So instead of just having the one discrete random variable, well, we now have two or more. So the joint probability mass function, the word joint is there, is a complete listing of these probabilities. What does this mean? Well, I have to tell you what is the probability that X is something and Y is something at the same time. So in other words, the table kind of looks like a grid. Okay, and I'll flash to an example right now. Uh, there's one more. I'm so sorry. I didn't know there was one example hiding here. Okay. Forget what I wrote. Okay. Let's just finish this one. Okay. In a recent study, it was found that tickets averages. This must be a horribly old question or something because I'm sure they don't cost this much anymore. Anyway, if the average is 80 and the variance is 105, what would be the variance if I now put a 3% tax on all tickets? Do you know how to do this problem? What am I looking for? Var what? If X is the cost of a ticket, what am I looking for? Var. A 3% tax is tantamount to saying that the cost of the ticket now is going to be what? 1.03x. So what are you looking for? You're looking for var of 1.03x, which according to the rules of variance, what is that? 1.03 square var x. That's right. So it's not a difficult problem at all. Something like that. Okay, easy enough. Okay. So anyway, so okay, so let me just flash to an example. When we talk about jointly distributed random variables, I'm talking about a probability distribution like this. In other words, now you have x and y and the joint probabilities. What does this point one mean? This means the probability that x is 0 and y is 0 together. Okay, so that's the shape of a jointly distributed random variable. So you see, The joint probability mass function of a discrete random variable is defined as the listing of all joint probabilities. Okay. Okay. What's the cumulative joint CDF? Well, now you have two things. When you have only one random variable, the CDF is just the accumulated probability for one of them. Well, now you have a second one to think about. Both happening together. X less than something and Y less than something else. So all this is just a generalization of it. But these things are not trivial to find, because when you look at your table, you have to be very, very careful. Let's pick up all the cases where this is true and this is true, and then try. Okay? We'll be revisiting these things again. So specifically, how do you find this for discrete random variables? It's quite easy. You add up those cases, add up all the probabilities where this is true, and that will give you the joint CDF, right? We can always derive the marginal probability distributions for X and Y by doing this. I'll explain. Do you agree with this? If I gave you the joint probability function, how do you marginalize and get back what it is for one or other of the other variables? If I want to know the probability that X is something, isn't it correct to add up all the cases where X is this and Y is everything else? That's it. Why is it called marginal? Because it literally sits in the margin of a piece of paper. You draw a table, your X, it means add up all, and the answer appears in the margin. That's actually the historical basis for what is called. It sits in the margin of your table. You add up all the columns, all the Y's, and you get your marginal one, like that. All right. Same thing for Y. If I want to isolate Y, I add up the cases for X. You'll be surprised. These things are quite intuitive to do, but formula-wise, it can be a little bit confusing, so I want to introduce it right now. Right? It just means add up over all X's possible. Doesn't matter if some combinations don't exist in your table, then the probability is zero then. But you add up over the other variable that you're not interested in right now. Okay, let's do some examples. Yeah, I think we can. Okay. Example 90. Consider the experiment of throwing a fair coin and a fair dice simultaneously. So do you agree, first of all, the sample space is this? When you do these two things at the same time, these are the only things you can see. Either you get a head and then a score of 1 to 6, or you get a tail and a score of 1 to 6. So there are 12 data points, 12 points in the sample space. Can you find the cumulative, the joint CDF? See, capital F is a CDF. This, okay, let me explain the notation. Previously, when we introduced the CDF, we just called it capital F with nothing, because there's only one random variable. But now that you have two running around, this is the CDF of X and Y together. In math speak, comma is usually a replacement for saying and X and Y jointly together. What's the CDF at value 1 and 2? And the 1 refers to the X, the 2 refers to the Y. So when I say this, I mean this. This just means this. What's the probability that X is less than or equal to 1 and Y is less than or equal to 2? So the only way to do this is actually to think of all the cases where this would be fulfilled. And we have these fulfilled in these cases. Your X is less than or equal to 1, okay, when your number of heads showing, yeah. So basically, if your heads are just, either you get one head or you don't get a head, and your die score is 2 or less, 1, 2, 1, 2. Do you agree? These are the only 4 things in the sample space that fulfill this criteria. And you just add up those properties. Now, since these are all fair points and fair die and all that, all 12 of the things that could happen are equally likely. That's why each of these has a probability of 1 over 12. That is why your answer is 4 over 12. So this is an equally likely sample space because of the fairness of the points and the coin and the die. All right. This is a bit more clunky, this example. We'll look at another one. Okay, so here is a joint probability mass function. Show that, first of all, that this is even a valid joint PMF. Well, to show that, you must show that it adds to 1, which it does. These are the only things that can happen jointly. Some combinations of x and y cannot happen. There's a 0 probability that x is 3 and y is 0 at the same time. All right? Some combinations can't happen. Find the probability that there are more than 2 customers in line. Okay, so customers are represented by, X is the number of customers in line 1, Y is the number of customers in line 2. So if you want to know that there are more than 2 customers in line, can someone give me a phrase in terms of X and Y? What are we looking for? Anyone want to try? X is there are 2 queues, okay? And X is the number of people waiting in line in one queue. Y is the number of people waiting in another queue. If I say find the probability that there are more than 2 customers in line, what am I saying? Can you give this to me as a statement in terms of X and Y? I would think so, right? That's what it means, because that's what we want. So what you do, consult the table and find those cases where X plus Y is more than 2. So which of those qualify? So I'll just show one example. X plus Y more than 2. See, this combination will not qualify. Because 2 plus 0 is 2, it's not more than 2. But this one does, and I think you get the idea. So find out the qualifying combinations and just add them up. What about this one? The absolute value of X. In other words, the difference in the number of people in either queue is 1. That's what this would mean. Maybe one queue has more people than the other. We don't care which. But the difference in the number of people in the 2 queues is 1. That's the practical implication, because you don't care which line is longer. What's the probability that one line is longer than the other by 1%? That's what this is. So how do you do this? So I think most of you are at a state of mathematical maturity where you know that when you say this, what you mean is either this is true or this is true. When you say the absolute value is something, it means it's either that thing or the negative of that thing. You all know that, right? Obviously. And this is not an and, okay, please, because if it's an and, then the probability is 0. How can you be both things at the same time? It doesn't make sense. So it's an or. And so with an or, we have learned the rule of probability, or you can split up the probability by putting a plus. Why is there no intersection? You can't have these things happening together. You can't be both 1 and minus 1 at the same time. And so add up those cases that fulfill these criteria. Can you do this? Can you construct a marginal? Just do 1 or 2. Can you get just X alone? So first of all, you know that X can only be 0, 1, 2, or 3. So what's the probability X is 0? What's the rule? You marginalize. You add up the cases that you don't want. Add up over all possible Y's when you fix your X at 0. So is it obvious that the first entry should be 0.3? If you go back to the table. Okay, why? I'll show, right? Because if you look at the table of the joint, when X is 0, Y could be 0 or 1, but that's it. The other cases have no probability. So add these two together. That's it. It's as easy as that. So you can put the sum, if you want, in the margins here. So it's called a marginal distribution. All right. These ideas are very important to really solidify in your mind, because when we do the continuous version and calculus comes in, it can be easy to get bogged down with the math and not have the intuition of what's actually going on. But the concepts of marginal distributions is true even for non-discrete random variables, which we will get to. But it is easier to teach these things from a discrete standpoint, first of all. So you will know that your answer is correct because if you add up this, you should also get 1, because x is a random variable in its own right. So, and you can do the same for y. I don't think I do it. But y would be the reverse, well, the analogous thing. Okay, let's look at example 92. Hmm. Try this, all right? What's this, right? What's the probability x is 2 or more and y is 3 or more? Pretty easy, right? I think it's just only 2 entries qualify. That's it. X plus y is 4. Well, find the x and y's that fulfill this. So pretty basic. Hmm. So I want you now to do another income problem, very easy one. Construct a situation like example 92. Make a grid. Keep it simple and make sure you create a valid joint distribution and just ask questions like this. Maybe dream up something more interesting than what I have. Put some absolute values or whatever it is and answer those questions. Shouldn't take you that long, right? Go dream up your own jointly distributed random variable thing and generate a few questions like this. That's it. Okay. Now, you all know, right? X and Y do not have to share the same range. This is coincidental. It could be anything, just discrete, that's all. Okay. Okay, let's continue. If X and Y are independent, well, nice things happen. Then you know from laws of probabilities of independent events that the probability that X is X and Y is Y, you can split it up. So please be aware. I've had students who have misunderstood this. They thought that this is true for every joint probability mass function. No, it is not necessarily true. Only if you know that X and Y are independent, that this is the product of their marginals. If not, you cannot say. Be careful, right? So that's why the joint distribution is more important. That's the most general way you. So I just want to stress that you really appreciate what's going on. I know these examples are quite trivial, but this table is quite a deep thing to understand. When we display X and Y like this together, this is how they behave jointly. There is no promise that X and Y are independent. If they were, then this can be split as just find this probability times this probability. See, that's the point I'm trying to make. These probabilities can always be found, whether X and Y are independent or not, by working it slowly by looking at the table. But if you have independence, it's made simpler because you can make a product. In fact, you can prove to yourself that in your example that you generated, most likely you did not generate a set of independent random variables. You will find that your answer for this or questions like this would be different from if I took the product of this event times this event. If you just randomly, off the top of your head, generate a table, and most likely you will not create an independent set of random variables. So it would not be true. You would have to do this from scratch and look at it case by case. You cannot simplify by splitting them up as a product like that. So that's the point I'm trying to make here. It's quite important, okay? So if you have independence, then yes, you can say that the probability that they happen together like that is the product of their individual probabilities, i.e., the joint probability mass function factors. In fact, you can use this as a check for independence. But it's tedious, you know. Do you know if you want to show that X and Y are independent, it's not enough to show, hey, look, I found one pair of X and Y values where this is true. You have to show this for every single X and Y in the ring. It's not just, oh, I found one pair where this works. Yeah, another pair might not work. So you have to show it. So in other words, to show that something is not independent, it's easier. To show that something is not independent, find one counter example. If you can, here's a simple one. The probability x and y are both 1 is this. Is this equal to the probability that x is 1 multiplied by the probability that y is 1? It's not. That's one counter example, that's enough. But to show that two things are independent, you actually have to show for every possible combination of x and y values, and that is true. And so it's much harder to prove independence than to disprove it. It's not enough just to show one case. One case is enough to disprove something, but to prove something, I think this is pretty basic. If you've done bridge and all that, you've heard this kind of thing before. To prove something, you have to prove it true for all cases, and that's not such a nice thing to do. Very tedious. Again, because we know of the independence of, if you have independence, then this event and this event are independent. You can split up the probability like this. What are these? These are the marginal CDFs. This is how X behaves alone. This is how Y behaves alone. Right? Which again makes sense. When you have independence, whether you tell me anything about X or Y, it's as if you didn't tell me. And so there's a product like that. Again, because now we have two random variables running around, we have to put a subscript to show whose CDF is this. This is the CDF of X. This is the CDF of Y. Okay. Okay. So a few more examples. See, so you have a bunch of. How would you do this? Okay. So you see, I'm giving you the information that's joint. Notice that X and Y follow these rules. If you find this very confusing, just make a simple table. Make a joint table. I think that's actually easier. I don't know why this question is phrased this way. Make a table. So X could be 0 or 1 or 2. Oh, and Y could be 0, 1 or 2. So it's not a difficult table to make. Summarize this information as a table. Okay. 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, and 2, 2. So these are the only non-zero probabilities. How do you find the variance of X alone? See? So the only way to do this is to construct the marginal. You want the variance of X alone? Well, find X. How does X behave on its own? So you go find the marginal distribution of X. So you get this and this and this X alone by summing out Y. Then you need variance, right? So you find EX and EX squared, just like what we did maybe half an hour ago. So what's important about this example? This example shows you that if you have a joint, from the joint you get everything. You get all the marginals, because giving you joint behavior tells you more than giving you marginal behavior. Notice that you cannot construct the joint from a marginal. There's just not enough information. It's like a photograph that's high resolution. You can always resize it. But a poor quality picture cannot be upsized unless you are willing to use algorithms and imputation and things like that. But even then, it's not, that's also following a set of rules, right? It's like in between this pixel and this pixel, the color changes from this frequency to this frequency. Then you have a gradient rule or whatever, you can fill in the grid or whatever. It's extrapolation, interpolation, things like that. You cannot construct the joint from the marginal unless I tell you a lot about the way they behave jointly. But from a joint, you get everything. You can downgrade to a marginal, and then you get all the marginal information like that. Is this okay? So there's a bit of information theory here, a little bit. Okay. I want to talk about this one carefully with you. A study is being conducted in which the health of two independent groups of 10 policyholders is being monitored over a period of time. Individual participants in the study drop out before the end of the study with a probability of 0.2, and this happens independently of each other. Okay, so try to absorb this first of all. There's this clinical study, clinical trial being done, and people do drop out of studies. There's a likelihood of 20% that someone drops off from the study before it's over. What is the probability that at least 9 complete the study in one of the two groups, but not in both groups? So this is a joint problem because you now have how many people completed the study in group 1 is X. How many people completed the study in group 2 is Y. What do we want? Right? How do you work out this kind of problem? So if you want at least 9 completing the study in one group but not in both, I will give you a minute or so. Can you write this out in words? What probability statement should you have? Right? You want it to be that only one group has at least 9 completers, not both groups. How do you phrase this probabilistically in words, if you like? What does it mean when exactly one of the two groups has at least 9 people finished? Right? How do you do it? Right? Give it a think before I show you the answer. Right? You can use X and Y. You can define X to be number of people who finished in group 1, and Y is the number of people who finished in group 2. So what do you want? What can you phrase mathematically? What values of X and Y do you actually want? Do you agree that this is X more than or equal to 9 times Y less than 9? Not X, okay? Because how can X be two things at the same time? This is actually saying the first group has at least 9, and the second group has less than 9. And of course, that could happen in with the group switch, and therefore you can find one of these and multiply by 2 because of the symmetricity of the group. Now, do you agree with this one? Don't you have 10 in the group? For 9 people to complete, basically means 1 left. There are 10 ways where one person can leave. All right, and then the other 9 stayed on. The probability of staying on is 0.8. Leaving is 0.2. And what's this? Anyone? What's the 0.8 to the 10? Why is that important? Oh, that's a very bad choice of words, I realize. Remain. Don't say left. They didn't leave, they remain. This left is such a wow. I didn't know English can be so what's the word for it? Ambiguous. All right. Anyone? What's the 0.8 to the 10? What does that stand for? Anyone see what's 0.8 to the 10? Why is this necessary? Yes. Remain. That's right. Good. What Onion said. Okay, this is 9 people stayed on, one left. There are 10 ways this can happen. There's only one way this can happen. Everyone stayed on. And so that's it. And then why is there a 1 minus multiplied by it? Because this is the opposite of this event. This is 9 or more remain. This is less than 9 remain. Clearly, this is the complement of this. So you have 1 minus this. And then you multiply everything by 2 because this could happen in either case. All right. So this level of complexity should be something you are able to manage. Like that. Okay. Again, I will have you think about this. Let me see whether there's anything I need to mention anymore before. Okay, expected value. Okay, we'll come to that. So let's deal with this example first. Then we will. Okay, this an insurance company determines that n, the number of claims, is a random variable with this distribution. Notice what's the tacit assumption here is the n starts from 0 and goes on forever. This probability model assumes that n can go on with it doesn't have a finite range. All right. The company determines the number of claims received in a given week is independent of number of claims received in any other week. Determine the probability that exactly 7 claims are received in a 2-week period. So how do you do a problem like this? Well, I would do it this way. What we want is to call this random variable n1. This is number of claims in week 1. This is number of claims in week 2. And what do we want? We want to know the probability that week 1's number of claims plus week 2's number of claims is exactly 7. So I guess I included this example because it's important. This example is there to show you that sometimes, although we seem to talk about just 1 week, feel free to create your own random variables for other weeks. Because it says, the hint is, the number of claims in a week is independent of the claims received in any other week. So you feel free to create, oh, this is the number of claims in week 1. This is the number of claims in week 2. And we want to know the probability that in over 2 weeks, the total is 7. This part's quite easy. How do you get a total of 7? There's only a few ways. This is an integer allocation problem. 0, 7, 1, 6, 2, 5, 3, 4. And then you multiply everything by 2 because it could be the other way as well. And that's it. That's the only way to get 7 claims over 2. And then you slowly work out all the probabilities that you have to get your answer. That's it. We can ask you other things. For example, what is the probability that 1 week has exactly less than 2 claims and the other week has more than 5 claims? When you have the more than and all that, then you have the infinite sum and geometric series and all those kinds of things. The key point is due to the independence of the weeks, can split up the argument like that. That's what I'm trying to get at here. All right. Okay. I want to introduce now the expected value. Okay. Because we still have some time, let me just go into this one. How do you find the expected value if you have a jointly distributed set of random variables? Well, other than being notationally more sickening, it's actually not hard to understand. The expected value of any function of 2 jointly distributed things, it can be anything. It can be x plus y, x over y, x times y, whatever. The expected value of a function is take that function, dump it in here, scale it by the joint probability and add. Wow, okay, that's it. Don't like this formula? Don't worry. You don't need it. You don't have to do it. That's enough. This is okay. So let's give an example. I do have a note here. Maybe I'll just say this. If you ever need the expected value of a marginal x alone, this is also correct. Is it clear to the class why this has to be true? Sometimes students don't see it. Isn't x alone, I know this sounds weird, isn't this alone a function of x and y? It is. Isn't x x plus 0y? That you can turn any function of one variable into a function of two. And what did I just tell you? The expected value of a joint function of x and y is dump that function here, scaled by the joint probability. And that's exactly what I'm doing here. Why does this formula even make sense? Because the rules of summing over index like this is involving I. This is involving I and j, which technically means what? Can I slide xi out? Okay, because when you change a sum, the inner index is j. This is unaffected. You fix I. It's like the two clock hands. The minute hand goes completely around before the hour hand turns by 1/12 at the angle. Well, my brain just left for 30 degrees. So the point is, this changes faster than this. So you fix the outside index, then you change j. But because this is outside index, this actually can come out because it's common to all the j's. This comes out. What happens when you sum over all the j's? This thing, don't you get the marginal for x? So this collapses, that's the word. This formula collapses to your good friend expected value of x, if you really think about it. It does. All right, so we'll end today with one last example. Example 97. And this is, again, quite a simple one. Here's a joint. Okay, find the expected value of xy. Okay, how do you find the expected value of x times y? Well, follow the rule. Okay. You take all the possible values that x and y can be, multiply them together, and slowly cycle through all the possibilities. X and y could be 1 and 2 respectively. So take it in turns. 1, 1, 1, 2, 2, 1, 2, 2. Outside index changes slower. 1, then this is 1, 1 and 2, and then now 2 and 1, 2 and 2. You are given information about the joint probability. So just is this okay? So again, I have never told you anything about, can I say EXY is EX times EY? We'll end with this, okay? In general, EXY is not EX times EY, in general. Can anyone guess, when will EXY be EX times EY? Anyone have any guess? When would the expected value of xy be the corresponding ex times ey? Anyone have any guesses? There are times it is true, not in true in general, but when do you think it's true? This word starts with an I. When x and y are independent. And so we will get to that. For that. All right. So that's all for now. And I'll see you all on Thursday. So just so there's no confusion, because I sent an email to my other class and I think I got some dates mixed up. The exam is going to be the Thursday of next week, right?